Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is solving problems on the photoelectric effect part 2. We solved some very interesting problems in part 1 of the same topic, and um, this is a continuation of that in the sense that just we are going to solve more problems and some more interesting problems in this video. So a quick recap of essential concepts of the topic, that is the photoelectric effect, is not required again, since I've already discussed that in part 1 of the uh, video. So I would uh, suggest that anybody who is in need of a quick refresher of the essential concepts of the topic may refer to that video, and let's just straight jump into the problems and solving those problems. The first problem: calculate the number of photons contained in a beam of electromagnetic radiation of total power 180 watt if the source is an AM radio station of 100 kilohertz, and B, a 8 nanometer X-ray, and C, 4 mega electron volt gamma rays. So there are three different sources are given with the power 180 watt, and we have to calculate the number of photons in each of these three. Right, let's move ahead and do the first one, that is A, which is an AM radio station of 100 kilohertz frequency. 100 kilohertz, that is 100 into 10 power 3 hertz. Right, this is the frequency. Let's call that nu. Now what is the energy of each photon in such a radiation? Energy is Planck's constant h times nu, that is 6.63 into 10 power minus 34 times, this is 10 power 2, this is 10 power 3, so that is 10 power 5. So we end up getting 6.63 times 10 power minus 29 joules. This is the energy. Now the total power is given as 180 watts, so the number of photons in this case, number of photons is 180 watts is joules per second over 6.63 times 10 power minus 29 joules. That should give us the number of photons in this case. So that is going to be 2.71. So again, this is the final answer for the number of photons we are getting for this case. 2.71 into 10 power plus 30. Right, the second case, let's move to do that. B, that is 8 nanometer X-ray source. Here the wavelength lambda is given as 8 nanometers. The energy of each photon in such a radiation would be hc over lambda, and that is 6.63 times 10 power minus 34 times 3 times 10 power 8 for C over 8 nanometers, so 8 into 10 power minus 9. So if you do the math for this, you would get the energy of each photon in this case is 2.48 times 10 power minus 17 joules. Minus 17 joules. So here it is 10 power minus 17. Right? So that would mean uh, number of photons, in this case, number of photons is equal to 180 watt over roughly 2.5 instead of 2.48. I'm taking 2.5 here, and if I do the math, I'm getting 7.2 times 10 power 18 photons. Let's get to the third part of this thing, that is a 4 million electron volt or mega electron volt gamma rays. Here the energy, if you calculate, directly it is given, so we don't have to do any conversions from wavelength or frequency. It's directly 4 into 10 power 6 eV, and the number of photons in this case would be therefore 4 180 watt over 4 into 10 power 6 eV. The unit conversions are 180 joule per second over 4 into 10 power 6 times, from EV we are converting to joule unit, so it is 1.6 into 10 power minus 19. Right, this is the conversion factor. If you do the math here, you would get 2.8 times 10 power 14 photons per second. Right? That is the number of photons that this radiation factor is. Let's move on to the next one. The second problem: what is the maximum wavelength of incident light on a silver surface whose work function is given to be phi is equal to 4.64 eV, that can result in the production of photoelectrons? If the wavelength of the incident light is half this maximum wavelength, what will be the maximum kinetic energy of the emitted photoelectrons? So lambda max has to be calculated. For silver, this is given, the phi value is 4.64 eV. That is the work function of silver is given. And the condition is that if lambda is half, then what is the K max? That is the question, right? So let's start with phi. We know that phi is equal to h c over lambda max, and therefore lambda max can be written as hc over phi. We know these constants, so 6.63 into 10 power minus 34 is substituted for h, and for c we substitute 3 times 10 power 8 over phi is given as 4.64 times, we convert from EV units to joule units by multiplying it with electric charge, that is 1.6 into 10 power minus 19. Basic unit of the electric charge of the charge of the electron, that has to be multiplied for conversion from electron volt units to the joule units. This gives us lambda max as 2.68 times 10 power minus 7 meters. So this is the maximum wavelength which can produce photoelectric effect. Any wavelength higher than this, you don't see any photoelectric effect. So this can be roughly written as lambda max is equal to 268 nanometers. Right. Now the second condition is if this wavelength is halved, that means 268 is a wavelength we got for lambda max. If that is halved, so lambda becomes now 268 by 2. It is 134 nanometers. If this is done, what would be the Ke max? So we know that expression for Ke max, that is Hc over lambda minus Hc over lambda max. So if Hc is taken as a common factor outside of the brackets, you get 1 over lambda minus 1 over lambda max. We know the values for all the parameters on the right side, right? So 6.63 times 10 power minus 34 times 3 into 10 power 8 times 1 over lambda is 134, so 134 and nanometers, so 10 power minus 9 minus 1 over 268 for lambda max, nanometers again, so 10 power minus 9 meters. These factors are taken into account, and if we kind of simplify this and get the Ke max, you would get in joule units Ke max to be equal to 7.42 into 10 power minus 19 joules. If you again divide this by 1.62 into 10 power minus 19 to get the Ke max in electron volt units, you would get the 4.64 EV, right? So this is interesting that this value happens to be equal to the work function of the material as well, right? Let's move ahead. Third problem, in an experiment, the maximum wavelength for photoelectric effect in tungsten is found to be 270 nanometers, that is lambda max. Let's write it down, 270 nanometers. The experimenter needs photoelectrons of maximum kinetic energy 2 eV. Ke max of the emerging electrons is 2 eV. What frequency of light should be used to illuminate the tungsten surface in this experiment? The work function of tungsten is not given. If we collect it from the standard tables, we find that it is 4.63 eV. Fine. We have to calculate the frequency. What frequency of light should be used to illuminate? First, of course, we can even calculate the threshold frequency. The threshold frequency for this case, tungsten is in this case C over lambda max, because this threshold is frequency, that is the minimum frequency that will cause photoelectric effect, and that is velocity of light C over the maximum wavelength lambda max. This if you do, you would get 1.11 times 10 power 15 hertz, right? And then of course from here you can calculate this value, the work function. You don't have to take from the table sources. You can calculate this value because the work function is nothing but h nu threshold. Phi is equal to h nu threshold. So if you multiply this value with Planck's constant, you will get 4.63 eV. Of course, after conversion to UV units, so let me just proceed to do that. Phi is equal to 6.63 into 10 power minus 34 joule second times the frequency 1.11 into 10 power 15 hertz, that is per second, hertz is per second. So if you do this multiplication, you would get phi to be equal to 7.35 times 10 power minus 19 joules. Then if you kind of divide it by again the electron charge, you will get this in eV units as 4.63 eV. That is what we initially wrote out here. So that part has to be calculated. We can calculate it from the data given. Now once that is done, all we have to do is to calculate the frequency that is required for the photoelectric effect to occur. Because we now know from the photoelectric equation, Ke max is h nu minus h nu threshold. Of course, this is h nu minus 5, so we can write it like this also. Now we want the frequency value, so we take h nu to one side, and then we have Ke max plus h nu threshold on the other side. The maximum kinetic energy is provided in the data as 2 eV. So we can use that value for 2 of 2 eV here, plus h nu threshold we have calculated in eV units to be equal to 4.63 eV. So put together we get 6.63 eV. That is h nu in eV units. We want nu, so we can convert this 6.63 into joule units by multiplying by 1.6 into 10 power minus 19, and then dividing the Planck's constant, dividing it by Planck's constant, so 6.63 into 10 power minus 34, and we have equal terms getting cancelled, and our answer would be nu is equal to 1.6 times 10 power 15 hertz. That is the value of frequency that has to be used. Right. Let's move ahead to the next one. In a photoelectric experiment, it is found that a stopping potential of 1 volt is sufficient to stop even the most energetic photoelectrons when the light that is incident is of 260 nanometers wavelength. And a stopping potential of 2.30 electron volt is needed to stop all the photoelectrons when the wavelength is 207 nanometers. From these data, determine Planck's constant and the work function of a metal. So we need to find h from the given data, and then the work function phi of the metal. These are the parameters we need to calculate. So we have to set up two equations for this and then solve this up, right? The first equation obviously is for the First case where stopping potential is given as 1 volt. So let us say that the stopping potential for that case, first case, is V S 1, and the second case stopping potential is V S 2. Now V S 1 is given as 1 volt, V S 2 is given as 2.30 volt, right? And then we have lambda. First case lambda is lambda 1, let's call that, and that is 260 nanometers. Second case lambda, let's call that lambda 2, that is 207 nanometers. Therefore, we can write the photoelectric equation twice, right? The first case we would write that as Hc over lambda 1 minus Hc over lambda max for the given material. That will not change, so it is only lambda max. No need to suffix 1 or 2 there. EVS1 on the right hand side. And then we have another equation for the second case, and that would be similar except for the one suffixes will change to 2, right? So it is lambda 2 now here, and then you have same Hc over lambda max. On the right hand side you will have EVS2. Right, we need to calculate Planck's constant. So what we can do is, the first case here, let's say we take the Hc to the right hand side, right? Or divide the whole thing into its equation by Hc. We get 1 over lambda 1 minus 1 over lambda max is equal to EVS1 over Hc. Similarly, on the right hand side, for this case, second case, we get 1 over lambda 2 minus 1 over lambda max is equal to EVS2 over Hc. This one. So we can eliminate that from these two equations, right? By taking it to one side and bringing the other thing to the other side, and then they will both be equal to 1 over lambda max. That is done. Then what we have here is 1 over lambda 1 minus the first case, it is EVS1 over Hc, right? EVS1 over Hc is equal to 1 over lambda 2 minus EVS2 over Hc. Both being equal to, of course, 1 over lambda max. And then if we multiply the whole expression by the Planck's constant h, we will get h over lambda 1 minus EV S1 over C is equal to h over lambda 2 minus EV S2 over C. And then we can bring these two terms to the one side, that is the Planck constant terms. That would be h over lambda 1 minus h over lambda 2 is equal to EVS1, which is negative on the left side, goes to the right side as a positive number. And then we have E minus EVS2 over C already on the right side and stays there. And now we can take h as a common factor out, and then we have 1 over lambda 1 minus 1 over lambda 2 on the left side, multiplying h, and the right side does not change, right? Right side is remaining the same. Um, of course, we know the values for these two, right? Vs1 and Vs2. Vs1 is 1 volt, it's given as 1 volt, and then Vs2 is given as 2.3 EV, volt, or no, 2.3 volts. So if you take E over C as a common factor and subtract this, we get negative value 1.3 E over C on the right hand side. Right. Now if you kind of simplify this, H times lambda 2 minus lambda 1, the common um, factor would be lambda 1, lambda 2 here on the denominator, is equal to the right hand side remains the same. And now we don't know uh, know H alone, so H is equal to, all these numbers are known to us, right? So if you substitute all that and take them all to the right hand side, you get minus 1.3 E over C times lambda 2 and lambda 1. We have seen that lambda 2 is the question, it is given as 207 nanometers, and this is 260 nanometers, that is lambda 1. So if you subtract a smaller number from a larger number, again you end up getting a negative sign on the right hand side, that is negative 53. Let me go back here and do that. So there is a negative sign on the numerator here also, so that is negative 53 over, and the product of these two numbers, that is 207 and 260, that is 53,820. These two negative numbers will cancel, and then the rest of the values are known to us. So if you simplify this and work it out, you get for the given condition the Planck constant to be uh, 7.05 times 10 power minus 34 joule second. So that is on the higher side compared to the actual 6.63 value, but still for the given conditions this is the value you would get. We can also write the Planck constant in EV units. After conversion from joule units, you get 4.4 times 10 power minus 15 EV. Right, so that is the answer to that. Moving ahead to the next one. An average person can detect light with a minimum intensity of 4 into 10 power minus 11 watts per meter square for a wavelength of 550 nanometers, and this intensity, how many photons per second can enter if the pupil is wide open with a diameter of 9 mm? So how many photons can enter the pupil of 9 mm given the intensity of light and given its wavelength of 550 nanometers? So we have to calculate first how much light is being received by the eye. Let's say total power of light, right, received per second by the eye. That is, let's call the P. That would be equal to the intensity of light over a given area A, right? The intensity is given as 4 into 10 power minus 11. So we 4 into 10 power minus 11 watts per meter squared times the area, that is of the pupil have 9 diameter, millimeter diameter here, given right, 9 mm. So pi r square, let's say. Pi radius is half of this 9, that is 4.5. R squared, so another 4.5. And it is in mm, so 10 power minus 3. And for squaring it, that would get 10 power minus 6 into that. These are numbers we have for power. Therefore, the power is 2.55, to do the math, times 10 power minus 15 watt or joule per second. That's the power. Total power of light received by I every second. Now, the energy of the given photon we have to calculate from the 550 nanometer wavelength that is given to us. So, lambda is 550 nanometers. Energy of each photon is hc over lambda, that is 6.63 into 10 power minus 34 times 3 into 10 power 8 over 550 into 10 power minus 9 meters. And that is, if you do that, you get energy of each photon to be equal to 36 into 10 power minus 20 joules. Now we need number of photons per second, so we can write number of photons is equal to the energy that we calculated, right, from the power, that is 2.55 into 10 power minus 15 uh, joule per second, because it was in watt units, over this one. What we again here is 36 into 10 power minus 20 joules for the energy of each photon. You see, there is a 36 into 10 power for this one, and we have 2.55 into 10 power minus 15 for this other one. That is the total energy received by the eye. So that would give us number of photons per second, right? If you do the math, you would get about 7,000 photons per second. So in the question it is asked clearly, um, how many photons per second can enter. So the answer is 7,000. Let's move ahead to the next problem. If a point source of 100 watt 100 watt radiates light with a wavelength of 555 nanometer uniformly in all directions, how far from the source could this light be detected given the following data? So we have a point source and the wavelength is given as 555 nanometer, and it is emitting light uniformly in all directions. The question is, if the point source has a power of 100 watt, how far from the source could this light be detected? Given the following data, uh, data is, this is the wavelength at which the sensitivity of the human eye is maximum, that is 555 nanometer. The color is typically yellowish green for this wavelength. Assume that the eye is a dark adapted eye capable of detecting as few as 10 photons per second. So it's a good viewing condition, and eye is adapted to dark detection at then this can even detect 10 photons per second. The pupil of the eye can be taken to be about 7 mm in diameter here, right? These are the conditions that are given, and we are asked to calculate the distance at which a detection of photons can occur. from a point source that is only 100 watt, and the wavelength is given as 555 nanometer. So for a 555 nanometer wavelength, what is the energy of each photon? E is equal to hc over lambda. And for 555, if I substitute the values, I would get about 3.58 into 10 power minus 19 joule. That's what I would get. For a 100 watt source, how many photons this is? Number of photons is the total energy, which is 100 joule per second, over the energy of each photon, that is 3.58 into 10 power minus 19 joules. That would give us about 2.79 into 10 power 20 photons every second. That is the rate at which photons are being ejected by the source. Right. Now question is, for what distance? Let's call the distance as r. So for what r, this number would go from this number is at the source, so 2.79 into 10 power 20 is at the source. But at some distance, number of photons would reduce, that reach the eye would be only 10 photons, because that is the minimum detecting capability of a dark adapted eye. So at what distance this would happen is the question. So assuming that this is spreading uniformly in all directions, and therefore you can draw a large sphere at that particular distance, unknown distance r, you have now be able to calculate that distance, where these many photons would become 10 photons per second. So the diameter of the pupil is given as 7 mm. The area of the pupil, you can calculate that also, because that is also a small circular area that is detecting these photons. That would be pi r square for the pupil. R can be taken as 3.5 mm. So let's call that as capital R, the radius of the pupil. That is 3.5 mm. So let's take pi to be about 3.14 times 3.5 square. Right. And this large sphere of radius small r has a surface area where it hits the eye. This surface area of the sphere is 4 pi small r square. That would be the surface area of the sphere. So what we have here is to calculate r. On the left hand side, we have a photon density over a given surface to be 2.79 times 10 power 20 over an area of 4 pi small r square. On the right hand side, only 10 photons are received by the eye over an area of this capital pi r square, that is 3.14 times 3.5 times 3.5. We need to calculate r. So if you rearrange the terms here and go on to calculate r, all other values are known to us, you will find that radius, or the distance at which from this source about 10 photons are detected is about 9.2 into 10 power 3. The distance r at which this would occur is 9.2 into 10 power 3 kilometers. Such a large distance, or 9.2 into 10 power 6 meters. That is the distance at which about 2.8 into 10 power 20 photons reduced to about 10 photons The distance is about 9.24 into 10 power 3 kilometers. Right. So let's move ahead to the next problem. An orbiting space shuttle moved around Earth well above 90% of the atmosphere. It still accumulated an electric charge on its skin due in part to the loss of electrons caused by the photoelectric effect with sunlight. So there is a space shuttle that is orbiting the Earth, right? That is going around the Earth, let's say, and it is well above 90% of the atmosphere. So atmosphere kind of ends here, let's say. So 10% of atmosphere is left at that radius. The space shuttle is orbiting the Earth, and there are some loss of electrons on the skin of the material of the space shuttle, and that is caused by photoelectric effect with sunlight. So sunlight strikes the skin, and some electrons are lost. Suppose the skin of the shuttle were coated with nickel. So on the body of the space shuttle, let's say uh, the material is nickel, and it has a large work function, which has a relatively large work function. Phi is equal to 4.87 eV at the temperatures encountered in orbit. What is the maximum wavelength in the solar spectrum that could result in the emission of photoelectrons from the shuttle skin? What is the maximum fraction of the total power falling on the shuttle that potentially could have produced photoelectrons? So these are the two parts of this question. So first, let's proceed to calculate the um, lambda max from the work function value that is given to us. Lambda max is equal to hc over phi, right? So if you substitute the values that are known to us, namely the Planck's constant, the speed of light, and the given phi, and then convert, of course, the phi into joule units, you will get lambda in meters. That is, you get about 2.55 into 10 power minus 7 meters, or 255 nanometers. You will get for lambda max. Now, that is a maximum wavelength, right? So the first part is done. Okay. The second part is, what is the maximum fraction of the total power falling on the shuttle that could potentially have caused the emission of electrons? So the second part, what is the maximum fraction of the total power falling on the shuttle and that potentially could have produced photoelectrons? In order for this to be solved, you should know that for any wavelength lambda greater than lambda max, no photoelectric effect. No photoelectric effect can occur. So all the wavelengths that are having wavelength less than lambda max, that would cause photoelectric effect, right? So it is that fraction of the light from the sun, because sunlight is causing the photoelectric effect here. So it is that fraction of the sunlight having lambda less than lambda max that would cause the photoelectric effect and the ejection of photoelectrons here. And that fraction of power is calculated from the black body spectrum uh, data, and that would be calculated from the total area of the Planck's curve in the black body spectrum, right? So we kindly recollect that the black body spectrum resembles something like that, and then you have wavelength, let's say on the x-axis in this case. Then we have to calculate now a particular value, which is lambda max here, let's say, all values of lambda to the left of this lambda max, that is lambda less than lambda max, that causes the photoelectric effect on the skin of the spaceship, right? Let's call that range of wavelengths as del lambda here. All lambdas less than lambda max, let us call that range as del lambda. And we have to calculate the area under this Planck curve, particularly this region, to get the fraction of the power, right? So the question is the fraction of maximum fraction of the total power is asked, right? So that would be fraction would be area under the curve that is this black body curve or Planck's curve having wavelength less than uh, having lambda less than 255 nanometers, because we have calculated lambda max to be equal to 255 nanometers. So that is that area over the total area of the curve, right? That is a fraction. This area over that area gives the fraction. So total area under the curve. That is the entire thing, right? So this particular area divided by the total area, that would give us the fraction. Now we know that from Stefan Boltzmann law that the total area under this curve gives a power, and that is denoted as R is equal to sigma times uh, T power 4, where sigma is the Stefan Boltzmann's constant. So this constant is known. The temperature of the black body, in this case the sun, is taken to be about 5800 Kelvin in this case. That's a standard number. We can take that and substitute here to get the total power R. And if you do that math, you would get R to be equal to about 6.42 into 10 power 7 watt over meter square per meter square. Sigma is, we know, the standard Stefan Boltzmann constant, that is 5.67 into 10 power minus 8 for that. What about this is for the denominator, right? This whole thing. What about the numerator, that is the area under the curve having lambda less than 255? For that, we have to calculate the numerator would be u lambda del lambda. That is over a range del lambda. What is the area? That is given as u lambda del lambda, because this y-axis is u lambda. It's spectral density, energy density there, right? Right. Now we have to take somewhere lambda here. What is the lambda that we are talking about here in this case? Because we are having a range of lambdas here. We can take somewhere on the halfway, that is 255 nanometers is the lambda max. All lambdas less than that we are considering. The mean would be somewhere in the middle of this. That would be, let's say, 127 roughly, 127 nanometers. Right? So we can take lambda to be about 127 nanometers roughly, and then proceed on to calculate this, because we know that this u lambda del lambda is from Planck's formula. We can write it as 8 pi hc times lambda power minus 5 over e hc lambda kt minus 1. This is Planck's law. So using Planck's law, we can calculate the energy density over this particular range, the spectral energy density, and that can be used to calculate the numerator here, right? So the numerator gives us the area under the curve having wavelengths less than 255 nanometers. So we have to substitute here for u lambda del lambda u, we have taken lambda to be 127 in this case, and then del lambda we know is the range, entire range, that should be 255. And then we know that on the right hand side we would have the entire 8 pi hc lambda power minus 5, so that is 127 times 10 power minus 9 for nanometers power minus 5, and the denominator we would have exponential hc. I'm not putting the numbers here because it would be too clumsy here. So kT, Boltzmann constant times the temperature. Temperature already I mentioned. We have to take about 5800 Kelvin. Hc lambda kT, rather lambda kT minus 1, right? So if we, this is of course times del lambda also. This del lambda is there still, so del lambda. If we do the calculation here on the uh, so if you do the calculation here, you would get 1.23 times 10 power minus 4 joule per meter cube. That is the energy density units, right? So this is what you get. Now please recollect from our lecture on black body radiation, where we have mentioned that there is a relationship between the R and the U, right? So R, here it is from all wavelengths from 0 to 255 nanometers is equal to C over 4 of U lambda D lambda. Of course, here is del lambda. So this is the factor that is there for this relationship. So if you divide both sides by R, you get R 0 to 255 over R is equal to C 4R U lambda del lambda. Now on the right hand side we know C, we know U lambda del lambda, which we have calculated here, and then we also know R, we have calculated in the previous step using the Stefan Boltzmann's law. We have calculated R as well. So if we substitute those values here, you would get the left hand side, and that is the fraction of the total power. So the total power is R actually, which we have calculated, but the fraction is up to a particular wavelength of 255. So that is R up to 255 over the total power. That would give the fraction, and that fraction can be obtained from calculating the energy density fraction, and then of course multiplying that with the C over 4, and of course to get the fraction we have divided by R on the left side, and therefore we divided by R on the right hand side as well. And then if you put in the numbers for C, for R, and for U lambda del lambda, which we have calculated in two different steps, we will get the final answer as 1.4 times 10 power minus 4 units with a fraction. So that is a fraction of the total solar power that gets converted to photoelectrons in this particular case, right? So let's move ahead to the next one. How many visible photons are radiated per second from a 100-watt bulb if 5% of it is radiated in visible spectrum? What is the flux of photons at 2-meter distance if the bulb is a point source radiating equally in all directions? We have a 100-watt bulb and only 5% of it is radiated in visible spectrum. How many visible photons are radiated per second? That's the first part of the problem. The second part of the problem is what is the flux of photons at 2-meter distance if the bulb is a point source radiating equally in all directions? So first let's calculate the number of photons for the first part. Number of photons we know is the um, total energy over energy of each photon. So let's call that photon energy. Total energy over photon energy. Now visible spectrum, so average wavelength we have to take, right? So we can take the average wavelength for this particular case to be, let's say, about 500 nanometers for the visible spectrum, because we know that visible spectrum varies from ranges from 350 nanometers typically to about 750 nanometers, let's say roughly, or maybe 700, let's say. If about 350 to 700, one can take roughly about 500 or 550. For convenience, let's say I take 500 here, 500 nanometers, let's say. You can even calculate for 550 also. What is the energy of photon? That is, for this particular wavelength, energy of the photon is hc over lambda. And for the given lambda of 500, let's say, that would be 6.63 into 10 power minus 34 times 3 into 10 power 8 over 550 nanometers, so 550 into 10 power minus 9. If you do this math, you would get the energy of single photon to be about 3.98 into 10 power minus 19 joule, right? Number of photons, let's say n, is equal to the total energy radiated by the bulb, which is 100 watt, over this, but here only 5% has to be taken, so that is 5 watt only. So 5 watt or 5 joule over every second, divided by the energy of each photon, that is this. If you calculate this, you get 1.26 times 10 power 19 photons. Remember, the bulb is 100 watts, but only 5% of it has to be in the visible spectrum, and that converts, the photometric conversion occurs. And therefore, here we have 5% of 100 is 5 watts, so that we have to take and calculate the number of visible photons per second, and that is 1.26 into 10 power 19 photons. Right. Now this answers the first part of the problem. Now, what is the flux of photons at 2-meter distance if the bulb is a point source radiating equally in all directions? So here we need to calculate the flux of, at a distance of 2 meters. So at a distance of 2 meters from the source, that is equally radiating in all directions, we have a surface area that is equal to 4 pi r squared, right? And therefore, at that distance, what will be the flux? That area we have to first calculate. So that is 4 into 3.14, or we can even keep it as pi, times this r is 2 meters they have given. So 2 square is 4. So it is 16 pi. That is area, or surface area of a sphere at that particular distance of 2 meters. Therefore, flux is very simply calculated as flux of photons is the total number of photons which we have calculated at that distance to be 1.26 times 10 power 19 every second over this area, so that is 16 pi. If you divide this, you would get 2.5 into 10 power 17 photons every second. That is the rate at which photons are arriving at a distance of 2 meters, so that as an area factor as well over every second. You can see that we have a meter square on the denominator for this area. Therefore, this is the answer. Right. Let's move ahead to the next one. To dissociate the sodium chloride molecule into neutral sodium and chlorine atoms, an energy of 4.26 eV needs to be supplied, which is the bond energy. What are the minimum frequency and maximum wavelength of the photon necessary to dissociate the molecule? So you have sodium chloride molecule, its uh, bond energy is 4.26 eV. You have to supply that much energy to dissociate it into sodium and chlorine molecules. And in order to do that, you need energy, that is photon energy, to be having certain minimum frequency and maximum wavelength. What is that? What are the values of minimum frequency and maximum wavelength? That is what is asked. And what part of the electromagnetic spectrum this photon would belong to? Okay, so we can start from the bond energy that is given to us as 4.26 eV of sodium chloride molecule. And in order for this dissociation to occur, we need to supply a photon having the same energy. That means we are kind of getting this as a work function. This is work function typically equivalent to that. And therefore, in a photoelectric case, if this is attributed to the work function, then we can easily get the minimum frequency as uh, work function over Planck's constant. The work function is 4.26 times 1.6 into 10 power minus 19. For Planck's constant, 6.6 into 10 power minus 34. If you do the numbers here, you get lambda threshold or lambda minimum, both are same. That would be equal to 1.03 times 10 power 15 hertz. And the corresponding wavelength, which is lambda max, is equal to C over lambda minimum or lambda threshold, minimum or new threshold, and that would be equal to 2.92 into 10 power minus 7 meters or 292 nanometers. So these are the values that are asked in the first part. Now, what is the electromagnetic spectrum? What part of the electromagnetic spectrum that we belong to? We know that this is less than 350 nanometers from where visible typically starts, visible spectrum starts. So this is in the ultraviolet region. This is in the UV region of the electromagnetic spectrum. That is the answer to the second part of that question. Let's move ahead. The eye will perceive a flash if 60 photons arrive at the cornea under optimum conditions. If the wavelength of the light is 550 nanometers, how much energy is this in joule units? So here the sensitivity of the eye is given to be about 60 photons. And if the lambda is 550 nanometers, right? How much energy is in joule units? So we have to calculate the energy of the photon for a given value of lambda. That is E is equal to h nu or hc over lambda. Let's call that energy of the photon EP. If you do substitute the numbers here, you would get this to be about 3.61 times 10 power minus 19 joules. That's what you get. Now 60 such photons, this is photon of the energy of each photon. Now 60 such photons means total energy is E is equal to 60 times EP, and that would be 2.17 times 10 power minus 19 Okay, 16 EP, so this is 10 power 17. 3.61 times 60. So 10 power minus 17 joules now. So that is the answer to this question. How much energy is this in joule units? 0.17 10 power minus 17. Let's move ahead. Using only the data provided, find the work function of potassium. Compute a value for Planck's constant. So this is the question. What is the data that is provided here? When a light of wavelength of 450 nanometers is incident on potassium, photoelectrons with stopping potential of 0.52 volt per emitter. If the wavelength of incident light is changed to 300 nanometers from 450, the stopping potential increases to 1.9 volt from 0.52. Speed of light is given as this, and charge of electron is also given as the data. So this is the data that is provided, and we have to calculate the work function of potassium and then compute a value for the Planck's constant from there on. Of course, for the given data only, we have to calculate that. So the two things that are needed in this is, first is the work function of potassium. Let's call that phi of k. And then the second part is the Planck's constant h. Now photoelectric equation we have to set up, and then we can solve this one. We know that E times the stopping potential, let's call that Vs1 in this first case, is Hc times 1 over lambda 1 minus 1 over lambda max, because we have two cases here. So I'm straight away writing it out. EVS2 here is equal to Hc 1 over lambda 2 in the second case, second wavelength is given, and then lambda max does not change for given material, so that is again lambda max. So we have set up two equations, equation 1 and 2, based on the photoelectric equation for the given two cases. We can now try to write down what is known to us, E on the left side, times the first Vs1 is 0.52 volt, which is equal to Hc. Lambda 1 is given as 450, so Hc over lambda 1, that is 450 nanometers. The Hc, if it is taken inside here, and then the second term also has Hc over lambda max, that is 5. So let us write it out as 5. Let's call this as again equation 1. Just we have substituted numbers there. Then we have E times 1.90, that is for the Vs2, is equal to Hc over this wavelength now is 300, so 300 nanometers minus 5 again. 5 remains the same for the case, given case that is potassium. So what we can do is, these two equations we have, we can multiply the first equation by 450 nanometers over E, because we have a 450 in the denominator here and E on the numerator here, so we can kind of get rid of those things by multiplying this, and multiply the second equation by 300 nanometers over E. So we do these two multiplications, what we will get is, on the left side already E times 0.52 is there, E gets cancelled, so we have 0.52, and we are multiplying by 450 nanometers, so that is 450 nanometers. On the right side we have Hc over 450, that 450 gets cancelled, but we are dividing by E, so we get E there, minus extra on 5 is there, which we multiply with 450 nanometers over E, that remains there. Now let's call that equation as 3. Similarly, if we do for the equation 2, by multiplying it by 300 nanometers over E, we get 1.90 times 300 nanometers is equal to Hc over E minus 5 times 300 nanometers over E. This, let's call that as equation 4. Now if we subtract 3 from 4, that is 4 minus 3, if we do, we get 5 over E, that is these two terms. 450 minus 300 nanometer units in both cases is equal to, on the other side, these two terms get cancelled when we do subtraction. Of course, this is from this to this, so this minus sign becomes plus. That's why here we have first term. Second term will have a minus because this already has a minus. Here, on the other hand, this is going to be 1.9 times 300 minus 0.52 times 400. 450. Of course, nanometer units here. Alright, so we can now do the manipulation to get 5 over E on one side. So 5 over E, if we do, that would be, this is 150, right? This point. So the denominator here is 150, which goes to the right hand side as 150 here. And these two, if you do, you get 570 minus 234. That is 336. 336 over 150 is 2.24. So 2.24 volt. That is the unit you will get for this 5 over E. So finally, phi is equal to 2.24 E. So in electron volt units, this is the value for work function that you will get. Now we have to calculate the next step, that is Planck's constant, as the second part of this problem, right? In order for that to be done, what we can do is, from the first equation that we got, we set up two equations here, right? The first equation, go back and check here, this is the one, E times 0.52, where we have a term Hc 450, right? That we can keep it in one side and take this phi to the other side and write it down now. So Hc over 450 nanometers is on the left side now. 0.52 times E plus phi on the other side. From there we can get H easily, right? So H is equal to, all we have to do is multiply these two. So 0.52 E plus phi multiplied by this denominator, which goes to the numerator there as 450 nanometers over C, which is 3 into 10 power 8. Numerator in the left side, and it goes to the denominator on the right side, and that we know the values, know all the values. Phi is something that we calculated as 2.24 EV in the first part of the problem, so that we can substitute directly there. And do the manipulation, we will get H as very close to the actual value. So we get 6.62 into 10 power minus 34 joules. Planck constant. So we get very close to the actual value. Right. So let's move to the next one. Find the momentum of the following entities and express the values in both EV over C and kilogram meter per second units. So momentum units EV over C as well as kg meter per second for the given entities. That is a 10 MeV gamma ray, a 25 keV X-ray, and a 1.0 micrometer infrared photon. Finally, there is also a 150 megahertz radio wave photon. So we have to calculate the momentum of these entities and express the values in both eV over C and kg meters per second unit as well. So let's take the first case. First is the energy is given as 10 MeV gamma ray photon. That is 10 into 10 power 6 eV or 10 power 7 eV. And we want the momentum. So we know that for a photon, P is equal to E over C. And we have here 10 7. So 10 power 7 EV over C. That is the momentum for the photon. Now we have to also get this in kilogram meter per second units, right? For that we have to do subtraction. So the 10 power 7 EV we have to convert that into joule units. So we have 10 power 7 EV times 1.6 times 10 power minus 19. That becomes around joule units. That over C. C of course we have to now convert into meters per second. So we write 3 into 10 power 8 meters per second. If we do this, we get momentum. Of course, here joule units is nothing but right kilogram meter square per second square. So that if you do, you will get kg meters per second as the momentum units finally. If you do the relevant math, you would get finally the number as 5.3 into 10 power minus 21 kg meters per second. That's the value for this. Part B is a 25 keV X-ray. For this 25 keV X-ray, momentum is very simply P is equal to 25 into 10 power 3 per keV EV over C. This is the first in the units of EV over C. That is done. Again, if you do the kg meters per second units, you will find that that is equal to same calculation we have to repeat. So I'm not going to do that here. That is, you have to multiply that by 1.6 into 10 power minus 19 and divide it by 3 into 10 power 8. I'm going to just give the final answer as 1.33 into 10 power minus 24 kg meters per second. Now part C. Part C is a 1 micrometer infrared photon, infrared ray or infrared photon. What is its energy? This is in wavelength lambda, right? So we have to calculate that E is equal to hc over lambda. Substitute 1 into 10 power minus 6 meter in the denominator, and h and c values if you substitute, you would get the energy as in joule units 1.988 into 10 power minus 19 joules. If you calculate that in EV or convert that into EV units, you will get E is equal to 1.24 EV. So we calculated the energy there. Then we can now do the momentum. P is equal to E over C. Therefore, 1.24 EV over C. And then in kg or kg meter per second units, we can convert this P is equal to 6.63 into 10 power minus 28 kg meters per second units. That's what we get. The last part of the problem, where the wavelength of the frequency rather of the radio wave photon is 150 megahertz. So this nu is equal to 150 into 10 power 6 hertz. Using this value, we can calculate the energy as E is equal to h nu, and in joule units, you would get 9.95 into 10 power minus 26 joules, and in EV units, if we convert this, you would get 6.22 into 10 power minus 7 EV. Momentum, therefore, P is equal to 6.22 into 10 power minus 7 EV over C. And then momentum in kg meters per second units, if you want to, we'll do it as 3.31 into 10 power minus 34 kg meters per second units. So these are the required values. Right, let's move to the next problem. What is the wavelength of an X-ray photon of energy 10 keV? What is the wavelength of a gamma ray photon of energy 1 MeV? What is the range of energies of photons of the visible light with wavelengths from 350 nanometers to 700 nanometers? The first is a 10 keV X-ray photon, right? Whose wavelength lambda is equal to hc over E. And that, if you substitute the numbers like 6.63 to 10 power minus 34 for H and 3 into 10 power 8 for C, and then the given energy is 10 keV, so I say 10 into 10 power 3 for the kilo electron volts, okay, 10 power 3 times in conversion to joule units, I do 1.6 into 10 power minus 19 here. If you work this out, you would get about 1.24 into 10 power minus 10 meters, or 1.24 angstrom units. Right. Next, part B. What is the wavelength of a gamma ray of 1 MeV energy? Again, the same formula is to be used if you apply that. So if you do the math here, you will get 12.24 into 10 power minus 13 meters, which is 1.24 into 10 power minus 12 meters, or 1.24 picometers. Or in terms of nanometers, if you want to express, 1.24 into 10 power minus 3 nanometers. Similarly here, 0.12 nanometers. Right. The next part, C. What is the range for the visible spectrum having wavelengths from about 350 to 700 nanometers? So if you substitute lambda for 350 here, nanometers unit, if you do, you get about 3.55 eV. And then if you do same formula for 700 nanometers, which is the other end of the visible spectrum, you would get about 1.78 TeV. Right. Let's move ahead to the next one. A metal surface has a photoelectric cutoff wavelength of 325.6 nanometers. It is illuminated with light of wavelength 259.8 nanometers. What is the stopping potential? So we have lambda max here, which is 325.6 nanometers, and we have a lambda here that is 259.8 nanometers. We are being asked to calculate the stopping potential, Vs. So we know that from photoelectric equation, EVS is equal to Hc times 1 over lambda minus 1 over lambda max. If you substitute these numbers here, you can get Vs. Vs is Hc over E times 1 over 259.8 into 10 power minus 9, 1 over 325.6 times 10 power minus 9. If you work this all out, you would get the potential to be about 0.96 volt. That's the answer you would get. The cutoff wavelength for the photoelectric effect in a certain metal is lambda max, that is equal to 254 nanometers. Part A, what is the work function of the metal? Then B, with the photoelectric effect be observed for lambda greater than 254 nanometers or for lambda less than 254 nanometers. It's a very simple question. We have to just calculate phi. Phi is equal to Hc over lambda max, right? So if you calculate phi using the formula that we have been using in several problems, we would get about 4.89 eV. Of course, you have to convert this into from joule units to eV units. If you do the conversion, you get this value. Now the question is, since lambda max is 254 nanometers, what is the range in which we would get a photoelectric effect? You would get only for lambda less than 254 because it is lambda max. You cannot exceed lambda max, so you have to be having wavelengths less than 254 nanometers in order for photoelectric effect to take place. Right, so that's the conclusion there. Verify whether the following statement is valid or not. If not, what is a valid statement? Statement is the maximum photoelectron energy Ke max is proportional to the frequency nu of the incident light. This is the statement that is given. Is it correct to say this? Is the question. The answer is no. This is not directly proportional to nu itself. We know that from the photoelectric equation, the kinetic energy maximum, that is Ke max, is equal to the energy of the incident photon minus the work function. So this is also a part of the equation. So it is doing kind of an offset here, phi. So it's an offset term here, right? So it is not a direct proportionality between the two. Since there is an offset term, we can only say that Ke max is not directly proportional to nu, but Ke max is linearly dependent on nu, and of course proportional to the difference in the frequencies, because we know that phi is h nu h, right? threshold frequency. So nu minus nu th is present here. That is, you can write this equation again as Ke max is equal to h times nu minus nu th. That is, this can be written as h nu minus h nu th. H being outside the bracket here, the proportionality factor is the constant, is the Planck's constant. So Ke max becomes proportional to the difference nu minus nu th. So that is the correct way of, you know, uh, expressing the relationship between the maximum kinetic energy and the frequencies involved here. So this is not exactly a valid statement. Right. Find the energy of a 700 nanometer photon. Very simple. E is equal to hc over lambda. So if you substitute 700 nanometers there, you would get E to be equal to 1.78 eV. You would of course get in joule units. You can convert that into units. That's the answer. So it's units. The frequency of a 1 kilowatt radio transmitter is 880 kilohertz. What is the rate of its photon emission? What is the rate here? Rate is nothing but the number of photons that it emits per second, right? So how many photons, let's say, question is how many photons per second does it emit? That's the question. Now energy is given as 1 kilowatt. So we can write power, power is given as 1 kilowatt. So energy is 1000 joule per second, right? Energy per second, rather, like say. Is this. Right, now number of photons we need. First we have to calculate the uh, photon energy from frequency nu. So E is equal to h nu. For 880 kilohertz, we have 880 times 10 power 3 hertz, and for h we have to substitute its value. We would get the energy per photon to be 5.834 times 10 power minus 28. That's the value you get. So number of photons per second that it emits. Directly we can take this rate and then substitute here. So that is 1000 joule per second uh, divided by this photon energy here, 5.834 times 10 power minus 28. So the answer is 1.71 into 10 power 30 photons per second. That's the rate of photon emission. Right. Let's move to the next one. The intensity of light from the sun, which is on an average at a distance of 1.5 into 10 power 11 meters away, is 1.4 into 10 power 3 watts per meter square on an area perpendicular to the direction of light, that is sunlight. Assuming that the sunlight is monochromatic with a frequency of 5 into 10 power 14 hertz, first is how many photons fall per second on each square meter of Earth's surface directly facing the sun. Calculate the power output of the sun and how many photons per second does it emit. So here how many photons are falling per second on Earth. So we have Earth here, sun, let's say, and over a small area, the rate at which the energy is received is given here over an area. The energy per unit area per second is 1400 uh, watts, and then you have how many photons does it emit and how many photons does it receive per second. How many photons per cubic meter are there near the earth? Here, how many photons are there in this region? Here, these are the questions for this given data. So what we have been given is the distance between you know earth and sun, 1.5 into 10 power 11 meter away, and then frequency is given, which is an assumption that a monochromatic radiation is received from the sun. We know that the wavelength uh, sun the wavelength that the sun emits is spread over a range of wavelengths, so it's not a single wavelength actually. So for the sake of this problem, we have to assume that it is a single wavelength and proceed to calculate. That is the assumption we have been asked to make. Right, let's start with the first part, A, which is calculation of the energy of the photon, right? That is based on the given uh, frequency, that is 5 into 10 power 14 hertz is given. So we say E is equal to h nu, and if you substitute 5 into 10 power 14 hertz there, the energy that you would receive is 3.32 into 10 power minus 19 joules. Joule units, you can have it. Now number of photons we have to calculate per second. So from the given uh, this thing 1.4 into 10 power 3, that is 1400 watts uh, per meter squared. We can calculate this by dividing this energy of photon and we can get the number there, and that would be 4.22 into 10 power 21 photons per meter squared per second. So how many photons fall per second on each square meter? So the answer to the part A is this: of Earth's surface directly facing the sun, right? Now second part, what is being asked there, the second part is the power output of the sun, and the distance between sun and earth is given, that is to be 1.5 into 10 power 11 meters, and the total power we can calculate, that is a power of 1400 watts um, per meter square is given, and over a sphere, let's say here the sun is emitting uniformly in all directions. At earth it forms a huge sphere of this radius, so we say that 4 pi r squared is the surface area of such a sphere. So the radius is 1.5 to 10 power 11, so 1400 times 4 pi times 1.5 into 10 power 11 whole square. This number, if you do, you get the total power that is uh, that will help us to calculate the answer for the part B. So 3.96 into 10 power 26 is the total power that is emitted by the sun. And then using this value, we can say that how many photons are emitted by the sun, we can calculate, because that is what is asked in part B. Calculate the power output of the sun, which we have calculated now, and how many photons per second does it emit. So the power output is calculated here to be 3.96 into 10 power 26, and the number of photons does it emit is calculated by using this power output, because this is in watt unit, it is joule per second, over the Energy that we have calculated for energy of photon, that is 3.32 10 power minus 90. That we have taken use here. So 3.32 into 10 power minus 90. So you can see that number of photons is huge here, right? So if you work out the numbers, you get 1.19 into 10 power 45 photons every second. This is the number of photons that sun emits every second. And okay, then the third part, that is part C. Let's say here near the Earth, how many photons are received? That's the question, right? How many photons are received near the Earth? So that is very simple. That can be calculated from because we have a rate here, right? What we have here is, see, um, the number of photons that falls per second on each square meter. It's for an area it is given of Earth's surface is directly facing the sun is calculated under the here. It is 4.22 into 10 power 21 photons. That's what we calculated in part A of this problem. Now if you divide this by the speed of light, see, we will get the answer for this particular part, right? Because we have here number of photons per unit area per second. We want number of photons near the surface so that can be calculated by just dividing it by velocity of light. So in the third part, if you see how many photons per cubic meter are there, there is a tip there, are there near the Earth. So that is 4.22 into 10 power 21 divided by C, which is 4.22 into, because the rate at which the photons reach is the speed of light. Sorry, the speed at which, because the speed at which the photons travel is speed of light, that is 3 into 10 power 8. From sun, this is the speed at which the photons travel and reach the surface of Earth, near the surface of Earth. And since we already have a number of photons over a given area per second, that is the rate at which the photons arrive, if we divide it by the speed of light, you would get the photon density, so to say, near the surface of the Earth. This number is 1.41 into 10 power 30 photons per meter cube. That is the answer to the third part of this question. Right, next problem. The maximum wavelength for photoelectric effect in tungsten is 230 meters, sorry, nanometers. What wavelength of light must be used in order for electrons with a maximum energy of 1.5 eV to be ejected? This is maximum K. Now what is asked? What is the wavelength lambda? That's the question. So we know for the simple photoelectric equation, we can get this. We want 1 over lambda. 1 over lambda max is given for tungsten. So we can use all this. This is one in EV. We have to do some kind of a EV to Joule conversion to finally get this out. So we can retain these things in one side and then take this HC to the side and solve this easily. So Ke max is 1.5 into 10 power nothing. So Ke max so Ke max is 1.5 eV. So 1.5 into 10, 1.6 into 10 power minus 19 for joule conversion. This HC we can just write it out as 6.63 into 10 power minus 34 times 3 into 10 power 8, and then 1 over lambda minus 1 over lambda max, which is 230 into 10 power minus 9. So if you do the math, we simplify and then take this term also to the left side and retain 1 over lambda on one side, you would get 1 over lambda to be equal to 0.56 into 10 power 7, and therefore lambda would be equal to 1.8 into 10 power minus 7, or 180 nanometers. That's the answer for this question. Right. Um, what is the maximum wavelength of light that will cause photoelectrons to be emitted from sodium, whose work function is given as 2.3 eV? And what will be the maximum kinetic energy of the photoelectrons if 200 nanometer light falls on a sodium surface? So here lambda max is asked, and then Ke max is asked for a given lambda. First part is lambda max for the given phi. So we know that lambda max is equal to Hc over phi, and phi of course has to be converted from eV to joule units to arrive at the lambda max in meters. So we say, if you do the calculations, you would get 540 nanometers. That's the lambda max you would get. Once you know the lambda max, you know that Ke max can be calculated by doing Hc over lambda for the given lambda of 200, and we have H minus Hc over lambda max. So Hc 1 over 200 into 10 power minus 9 minus 1 over 540 into 10 power minus 9. So if you work this out, you would get the maximum kinetic energy in EV units to be 3.92 EV. That's the final answer. So next question, 1.5 MW milliwatt of 400 nanometer light is directed at a photoelectric cell. If 0.1% of the instant photons produce photoelectrons, find the current in the cell. So the not all the incident photons produce photoelectrons here, only about 0.1%. That's the point. The energy of the photon can be calculated from the wavelength that is given here. So E is equal to Hc over lambda. So if you substitute the numbers, you would get this energy to be about 4.97, let's say, into 10 power minus 19 joules. This is energy of the photon in joule units. We want number of photons, right? Because this is given in milliwatt units. So we say number of photons of course there is per second also. It is 1.5 into 10 power minus 3 joule per second. over this energy of the photon, that is 4.97 into 10 power minus 19 joule. If you work this out, you would get about 3 into 10 power 15 photons, of course, every second. That is the number of photons that are being incident on the photoelectric cell. Out of this, only 0.1% is producing photoelectrons. So 0.1% of 3 into 10 power 15 is this number of photons, right? Is the number of electrons that are produced. And therefore that is 0.1 over 100 for percentage calculation. To do this, you would get 3 into 10 power 12 electrons per second. So these are the number of electrons that are flowing in the circuit per second, and therefore we know that the current, whatever the current is being asked, let's say, so current is charge for time, the rate at which charge flows. Here already the charge uh, flows uh, can be the charge that flows can be calculated, because that is number of electrons over a given time, right? So the number of electrons are 3 to 10 power 12. So that total charge is 3 into 10 power 12, that is the n here, times the charge of each electron is 1.6 into 10 power minus 19 coulomb. That gives us the total charge NERQ. That is over time already, second units are given there. So this is the current that we are going to get. If we work out the numbers, the current turns out to be about 0.5 microamperes, or 0.5 to 10 power minus 6 amperes. This is the value you would get. A metal surface is illuminated by a light of frequency 8.5 into 10 power 14 hertz, and that emits electrons whose maximum kinetic energy is 0.52 eV. The max is 0.52. And the same surface is illuminated by light of under frequency, which is 12 into 10 power 14 hertz. And this time the electrons emitted have a kinetic energy of about 1.97 eV max. From these data, find Planck's constant h and the work function phi, let's say, of the metal surface. So first, there are two cases, two frequencies are given here. New one, let's say, is 8.5 into 10 power 14 hertz, for which Ke max is given as 0.52 eV. Similarly, new 2 is given as 1. Sorry, the new 2 is given as 12 into 10 power 14 hertz, and then Ke max here is given as 1.97 eV. Right. So what we need to calculate is the Planck constant for the given data. So we can set up two equations here. The first equation, it says Ke max 1. This is for the first case. And second, let's say, is Ke max 2. So we can write photoelectric equation Ke max 1 for the first case is h nu 1 minus phi for the metal. That does not change, same surface only is used here. So the metal does not change. The second case is Ke max 2 is equal to h nu 2 minus phi again. So let's say these are equations 1 and 2. So you can subtract 1 from 2. If that is done, that is 2 minus 1 if you do, we get Ke max 2 minus Ke max 1 on one side and 5 common, so that would get cancelled. The other side you would have H as common factor, H nu 2 minus nu 1, right? Is what we get if you subtract 2 minus 1. On the left side, we know 1.97 is Ke max 2 minus 0.52. On the right side, H is what we should calculate, and the frequency difference is 8.5, 12. 12 is mu 2. So 12 minus 8.5 times 10 power 14 hertz. So that is the common for both, right? So if you do that further, uh, the difference on the left side for the stopping potential is 1.45 eV stopping potential, so we can write K max is eV, so K max is K. On the right side we have H now, and the frequency difference of 3.5 into 10 power 14 hertz comes to the denominator on the left side. So you would calculate H to be reasonably accurate of value of about 6.6 into 10 power minus 34 joules second. This is the value you would get if you work out these numbers. What about the second part of this question? From these data, find Planck's constant. That's the first part. Then the work function of the surface, phi a, where to calculate that. That is very straightforward. We can take any one of the equations and do it. Let's say the second equation we do. A max 2 is equal to h nu 2 minus phi. We want phi here. So phi is equal to h nu 2 minus Ke max 2. So we have numbers to substitute the values. You get phi is equal to 2.83 eV. We convert from joule units to eV units. You get this. So that completes the 23rd problem. Let's move on to the 24th. Show that it is impossible for a photon to give up all its energy and momentum to a free electron. So in the photoelectric effect, the electrons are bound to the metal surface. They are part of the metal surface. And when light is incident upon the surface, electrons are ejected. But if the electron is free and a photon tries to interact with that electron, it is impossible for a photon to give up all its energy and momentum to a free electron that is not part of any metal surface, that is not bound to any atom. Such an electron is a free electron. And if a photon comes and tries to interact with an electron, it is impossible for it to give up all its energy and momentum. Show that this is true. That's the question. This is the reason why photoelectric effect can take place only when photons strike bound electrons that are bound to the metal surface or to an atom in the metal. Right. So how to do this? Very simple. The photon's initial energy, from relativistic expression, let's say that the photon's initial energy is initial momentum P naught, let's say C. And if this is the case, what is the photon's initial momentum? Already we have mentioned that it is P naught. What is the expression for the P naught then? Photon's initial momentum is E over C. Since we have used the suffix 0 here, we will use for that also as 0. Of course, P naught. P naught is E naught over C. So this we know from relativity. Now, in electron's rest frame, What is the final momentum of the electron? Final momentum of the electron. Let's call that as PE, or P suffix E rather. That must be equal to the initial momentum of the photon, P0, because the momentum has to be transferred. If that is the case, this is it. Let's commonly call that as P now. And what is the final kinetic energy of the electron after it has received the energy from the photon? Final Ke of the electron. That is, let's say, E naught, because it has to have received the energy only from the photon, whose initial energy was E naught. So in the rest frame of the electron, it has to have received the energy as E naught only then, right? And that must be equal to this P times C, right? But we know that the electron energy, let's say E suffix small e, must be equal to, according to the relativistic expression for energy of the particle, its relativistic kinetic energy plus its rest energy. For electron, it's m suffix e, which is the mass of the electron, times c squared, right? From relativity, we know that we know that E squared, it is E suffix E squared, is Pc squared plus me c squared whole square. Let's say that is equation 2. Now if we compare 1 and 2, we would see that I can take a square of the first equation, I can square it up and then compare with this, right? So if I do that, on the left side I will have p squared c squared plus me squared c power 4 plus 2 pc mec squared. This is the effect of this squaring this equation 1. And on the right hand side we would have these terms pc, which is p squared c squared plus me squared c power 4. Now if you compare 1 to 1, you have this term, fine, you have this term, okay, but this is an extra term. And that tells us that our assumption that a free electron takes energy and momentum from the photon, that is both energy and momentum are transferred to a free electron, must be wrong, because of the extra term, which is 2 times Pc, which we cannot account for by assuming the photon is able to transfer both its energy and momentum to a free electron. That cannot be true. Therefore, we can conclude that it is impossible for a photon to give up all its energy and momentum to a free electron. That's the conclusion we can take. Right, so that brings us to the end of the solving problems on the photoelectric effect part 2. Hope to catch up with you soon on another interesting topic. Until then, it's bye from me. Thanks for watching.